The authors build their model on a set of simplifying assumptions. The coal is treated as a homogeneous, isotropic, elastic plastic material. The far-field stress is equal in all directions hydrostatic. The wellbore is a circular hole in an infinite plane strain condition, and the rock obeys the Moore-Coulomb failure criterion. Equation 1 states the Moore-Coulomb yield condition for the plastic zone around the wellbore. In plain words, it says that yielding occurs when the tangential hoop stress around the hole exceeds the radial stress by an amount that depends on the material's internal friction angle and cohesion. The larger the friction angle and cohesion, the higher the stress difference the coal can withstand before it flows plastically. Equation 2 is the equilibrium equation for a small element of rock in the radial direction. It expresses the balance between the change in radial stress with distance from the hole and the difference between the tangential and radial stresses. This is a fundamental static balance. The stress gradient must counteract the hoop stress to keep the element in equilibrium. Equation 3 gives the strain displacement relations for the axisymmetric case. The tangential strain is the logarithmic change in radius how much the circumference stretches, and the radial strain is the logarithmic change in thickness of a concentric shell. The use of logarithmic strain is essential because the model deals with large finite deformations, not just small elastic strains. Equation 4 introduces a dimensionless operation that scales the stresses by the elastic modulus and the cohesive strength. This normalization simplifies the mathematics and allows the yield criterion and subsequent equations to be written in a compact, dimensionless form. Equation 5 is the yield surface expression after normalization. It says that, in the plastic zone, the dimensionless tangential stress and radial stress must satisfy a linear relationship fixed by the friction angle, essentially a straight line in stress space that defines the boundary between elastic and plastic behavior. Equation 6 is derived by substituting the yield condition into the equilibrium equation. It results in a differential equation that relates the change in radial stress to the radial coordinate. Solving this equation gives the distribution of radial stress inside the plastic zone. Equation 7 is the explicit solution for radial stress at any point within the plastic region. It shows that radial stress increases as a power law function of the distance from the wellbore center, with the exponent controlled by the friction angle. The boundary condition is that at the wellbore wall the radial stress equals the applied wellbore pressure. Equation 8 gives the radius of the plastic zone, that is, the extent of the region around the wellbore that has yielded and entered the plastic state. It is expressed as the original wellbore radius multiplied by a factor that depends on the far field stress, the wellbore pressure, and the friction angle. The higher the far field stress or the lower the wellbore pressure, the larger this plastic radius becomes. Equation 9 describes the stress state in the elastic zone, which lies outside the plastic annulus. In this outer region, the rock is still behaving elastically. The equations show that both tangential and radial stresses decay with the square of the radius, reflecting the classic Kirsch solution for a circular hole in an elastic medium, but here the boundary condition at the elastic-plastic interface is used instead of the hole itself. Equation 10 gives the radial displacement in the elastic zone. It states that the displacement at any point outside the plastic zone is proportional to the stress difference between the far field stress and the stress at the plastic boundary, divided by the shear modulus, and decays as the inverse square of the distance. This is a standard elastic solution. Equation 11 is the continuity condition at the interface between the plastic and elastic zones. It requires that the sum of the radial and tangential stresses at that interface equals twice the far field stress. This ensures a smooth transition of stress across the boundary. Equation 12 then uses the yield criterion together with the continuity condition to determine the radial stress exactly at the elastic-plastic interface. This value depends only on the far field stress, the friction angle, and the cohesion, not on the wellbore pressure or the hole radius. Equation 13 defines two important displacements, the inward movement of the wellbore wall and the inward movement of the elastic-plastic interface. The shrinkage of the wellbore is the difference between the initial and current radius of the hole, and similarly for the plastic zone. Equation 14 introduces the non-associated flow rule, which governs how plastic strains develop. It says that the increment of tangential plastic strain is proportional to the increment of radial plastic strain, with the proportionality factor being the dilatancy coefficient. This coefficient accounts for the volume change dilation or compaction that occurs when the coal shears, a critical feature for soft, fragmented coals. Equation 15 is the differential form of the flow rule. By integrating this relationship, the authors link the change in radius to the plastic strain increments, effectively showing that the radial and tangential strain rates are related through the dilatancy coefficient. Equations 16 and 17 are compatibility equations obtained by integrating the flow rule between the initial and current configurations. They relate the current radii of the wellbore and the plastic zone to their initial values. The exponents involve the dilatancy coefficient, meaning that the deformation is not only large but also accompanied by volume changes. Equation 18 combines the plastic zone radius formula EQ8 with the compatibility relation EQ17 to express the current plastic zone radius in terms of the initial radius and the current wellbore radius. This is a key step because it eliminates the unknown plastic zone radius from the final shrinkage formula. Equation 19 calculates the displacement at the elastic-plastic interface using the elastic solution EQ10. This displacement is needed as a boundary condition for the plastic flow calculation. It tells us how much the interface has moved inward due to the elastic deformation of the outer rock. Finally, equation 20 is the central result of the paper, the wellbore shrinkage ratio, defined as the reduction in wellbore diameter divided by the original diameter, expressed as a percentage. This formula incorporates all the preceding derivations, the yield criterion, the stress distributions, the plastic radius, the flow rule, and the displacement compatibility. It shows that shrinkage depends nonlinearly on the material properties strength, modulus, friction, Poisson's ratio, and cohesion, on the far field stress which increases with burial depth, and on the wellbore pressure. The equation is the tool that allows the authors to perform the sensitivity analyses presented later in the paper, revealing which parameters have the greatest control over wellbore deformation. In essence, the mathematical framework transforms the physical problem of a yielding coal mass around a drilled hole into a set of coupled algebraic and differential equations, which are then solved in closed form to produce a practical expression for wellbore shrinkage, a quantity that can be used to guide drilling strategies in challenging coal seams.